Right, so if you look at this example here, again, as quick illustration, if you go and work out the eigenvalues of this matrix, then we can go and find a basis for the eigenspace corresponding to the value lambda equals -2, and that we found one vector there. And for lambda equals 0, you found 2 vectors, right? Now, if we throw these 3 vectors together, according to my previous theorem, that's going to be a linearly independent set. So this matrix has got a set of 3 linearly independent eigenvectors, right? Now, if you recall, there was a theorem that said that a matrix is diagonalizable if and only if it has a matrix of order of n by n matrix is diagonalizable if it has n linearly independent eigenvectors. In this case, this matrix A has got 3 linearly independent eigenvectors. Therefore, it has to be diagonalizable. Right, if you look at this example, this matrix has got 2 eigenvalues. And if you look at the eigenspace corresponding to lambda equals 0, and if you look at the eigenspace corresponding to lambda equals 1, then we see that in each case you've only got 1 vector. So if you throw those vectors together, that is going to be a linearly independent set of 2 eigenvectors. Unfortunately, if you look at any vector to be in a eigenspace of the matrix A, it's going to have to be either a linear combination of this vector here or a linear combination of that vector there. So therefore, you cannot find a set of 3 linearly independent vectors that correspond to distinct eigenvalues. So therefore, this matrix, you will not be able to diagonalize it. That gives us a nice little procedure for diagonalizing a matrix. So first we confirm that the matrix is diagonalizable by working out the eigenvalues. Then you work out the basis for each eigenspace, and then you merge these basis vectors together into a single set. We know this set is going to be linearly independent, and if the union of all these basis vectors has fewer than n vectors, then obviously the matrix is not going to be diagonalizable, because we cannot manufacture more linearly independent vectors than we've already done with calculating the basis. Okay. Then, once you've established that this is the case, all you need to do is you need to select the column vectors of your matrix P. These column vectors are going to be formed by taking eigenvectors from each eigenvalue and forming the required number of columns. And P will have n columns. Now this matrix P is definitely going to be invertible, and if I multiply A with P on the right hand side and P inverse on the left hand side, that's going to give me a diagonal matrix which is going to be which is going to have the eigenvalues lambda 1 up until lambda n, and therefore my matrix is going to be diagonalizable. So it's a pretty straightforward procedure, and it relies mainly on the results of theorem 1, 2, 3, and 4. Right, so the next example here is they ask us to determine whether or not the given matrices A are diagonalizable, and if they are, we need to find an invertible matrix P that will change the matrix A into a diagonal matrix. Now, if you quickly look at on first inspection, the matrix A is an upper triangular matrix, therefore it's we can easily determine its eigenvalues quickly. So for this matrix, obviously, because it's upper triangular, its eigenvalues are 1 and 2 respectively. Right, so considering lambda equals 1, we need to find all vectors x bar such that this is satisfied. Okay. And obviously x bar has to be 0. We want to find all non-zero vectors x. So this translates into this linear system that we need to solve. Right, so that linear system then corresponds to the following linear system. That's the case where minus 2y is equal to 0, minus 2z is equal to 0, and minus 1z is equal to 0. So therefore, that then x is your free variable, and y and z are both equals to 0, and that is where t is a real number. Okay, so the basis for the the basis for the eigenspace corresponding to lambda 1 is pretty much, it's the vector 1, 0, 0. Okay? So there's one vector in the basis for the eigenspace corresponding to lambda equals 1. So now we need to just look at the case where lambda is equal to 2. So for lambda equals 2, we need to find all vectors x, non-zero vectors x, such that this holds. And when lambda is 2, this becomes that there. Okay, and we want to solve this linear system. So that corresponds to, right, that corresponds to this linear system where z is my free variable. Okay, so there we have it. We've solved for x, y, and z. And so again, the basis for the eigenspace corresponding to lambda equals 2 is, okay, so we take that vector there, and that is our basis. Okay, so it's got one vector. Right, so since the distinct eigenvalues of A only correspond to two basis vectors, A is not diagonalizable. Right, looking at the next matrix, again, the eigenvalues are 2, minus 2, and 1 respectively, because it's an upper triangular matrix. So now we need to look at the eigenspace, the eigenspaces that correspond to each one of the eigenvalues. So we need to find all vectors x bar non-zero such that that holds. Okay, so that corresponds to this linear system that we need to solve. Right, so that corresponds to the set of linear equations, minus y equals 0, 4y minus z equals 0, and z equals 0. So therefore, x is a parameter, t, and y and z are both equal to 0. Okay, so therefore, the basis vector for the eigenspace corresponding to lambda equals 2 is going to be this that vector, the vector 1, 0, 0. Right, so the basis for the eigenspace corresponding to lambda equals 2 is the vector, that vector there. Right, so next we look at lambda equals minus 2. Right, so for lambda equals minus 2, we need to find all x's such that lambda I minus a times x bar is equal to the 0 vector, and that then becomes this expression. Okay, now just remember that the matrix A is that matrix there, and then if we work out minus a and we add lambda I to that, where lambda is minus 2, it's going to be basically minus 2 minus 2, which is going to be minus 4. Then it's going to be minus 2 plus 2, which is going to be 0 there. Okay, and then it is going to be minus 2 minus 1, which is that minus 3 there. Right, so that system then corresponds to that linear system there, and from there we've got that z is equal to 0. We can parameterize y as a real number t, and from that we can then solve for x as minus a quarter t. Right, so putting all that information together, we find the solution for the vector x, y, and z. So therefore the basis for the eigenspace corresponding to lambda equals minus 2 becomes just this vector here. Right. Okay, so that's the basis there. So now, lastly, we need to look at find the basis for the eigenspace corresponding to the last eigenvalue. So for lambda equals 1, we need to find all x's such that it satisfies that equation. Right, so there we've got that linear system. Again, recall what the matrix A was. Matrix A was that, so if we take lambda I, which is the 1 times the identity matrix, that's going to be 1 minus 2, which is that minus 1, 1 minus minus 2, which is 3, and 1 minus 1, which is that there, the 0 there, and there we've got the minus that minus that. Okay. Right, so from that corresponds to? Right, so that corresponds to this linear system. So the vector x, y, z can be solved as that. And so the basis for the eigenspace corresponding to lambda equals 1 becomes this vector, right? So we're going to take it and we're going to form our set there. That is a basis for the eigenspace corresponding to lambda equals 1. So there are three linearly independent vectors corresponding to three different distinct eigenvalues. So this matrix can be diagonalized. And how do we find the matrix that's going to do the diagonalization? So let's just look at our linearly independent set. If we take this vector from lambda equals 1, we place that in our set, and just note that that corresponds to lambda equals 1. We go to lambda minus 2, we select that vector there. We form that second vector. Right, and then we go back to our first eigenvalue, which is lambda equals 2. Take that, throw that into our set. That is our third vector. And that corresponds to lambda equals 2. Okay. Right, so we form our diagonalization matrix. Right, so take your first column, take your second column, you take your third column, that's your matrix P. Okay. And your diagonal matrix is going to be, right, that's my first entry on the diagonal. That's going to be my second entry on the diagonal, and my last entry on the diagonal is going to be 2, right? So that is going to be this diagonal matrix. Okay. Right, so let's look at the last one. A is, we look at number 3. Okay. So there's number 3. We need to quickly go and determine the eigenvalues there. Right, so if we look at lambda I minus A, that becomes this matrix here. And then looking at the determinant of this matrix sets up my characteristic equation. So that is basically the determinant of this worked out matrix. It's the determinant of that matrix. Okay. So here we can do a cofactor expansion along the last column, and that becomes lambda times the determinant of the matrix that I get by cancelling the last row and the last column, and so that is going to be lambda minus 2, 1, minus 1 and lambda. Okay. And that is going to be lambda multiplied by lambda times lambda minus 2. Okay, plus 1. Right, so that becomes that expression there, which is lambda lambda squared minus 2 lambda plus 1. Okay. Right, so that reduces to lambda times lambda minus 1 squared. Now what we do is, if we put that equal to 0, that happens if and only if the eigenvalues then become lambda equals 0 and lambda equals 1. Okay. Okay, so let's look at the eigenspace corresponding to lambda equals 0. So we need to find all x's such that lambda I minus a times x is equal to 0. Call what the matrix A was. There's my matrix A. Right, so lambda is equal to 0 there. So 0, 0 minus a, so that's going to become a 0 term there. Those are all going to stay 0. That's going to be a minus 1, and that is going to be a plus 1. Okay, so there we've got those terms there. Okay, so again, that corresponds to, right, so that corresponds to that linear system, and so that implies that this vector here, x, y, z, needs to be of the form and again that's going to imply my base is going to only have one vector. Okay. So the basis corresponding to lambda equals 0 is going to be the vector, there we go, okay. And for lambda equals 1, and all x's such that that expression holds. Recall what the matrix A was again. Alright, so there's my system. Right, so if lambda is 1, then it's going to be 1 minus 2, which is minus 1. It's going to be 1 minus 0, which is 1. And then it's going to be another 1 minus 0, which is 1. And that's going to be a minus, and that's going to be a plus. Okay, so therefore, right, so that corresponds to minus x plus y equals 0, minus x plus y equals 0, and z equals 0. So therefore, x, y, z can be solved as t times the vector 1, 1, 0. So what is the basis corresponding to the eigenvalue lambda equals 1? Right, so the basis corresponding to lambda equals 1 contains this single vector. And therefore, we've got two linearly independent vectors. Right, so the two eigenvalues of A correspond to two basis vectors. So therefore, A cannot be diagonalizable. Thus, A cannot be diagonalized. Right, so the next section we're looking at geometric and algebraic multiplicity. So what that just means is, if lambda is an eigenvalue of an n by n matrix A, the dimension of the eigenspace corresponding to lambda 0 is called the geometric multiplicity of lambda 0, and the number of times lambda minus lambda 0 appears as a factor in the characteristic polynomial of A, that is called the algebraic multiplicity of lambdas. Right, so theorem 5 talks about geometric multiplicity and algebraic multiplicity. It just says here that For every eigenvalue of A, the geometric multiplicity is less than or equal to the algebraic multiplicity, and also matrix A is diagonalizable if and only if the geometric and the algebraic multiplicities for each eigenvalue is exactly the same. Alright, so why is it that if we assume that A can be diagonalized, why does it then mean that the geometric multiplicity and the algebraic multiplicity of A are exactly the same? Well, remember the similarity transformation that I'm doing. Remember those conditions that remain invariant under that transformation. The first one is that the matrix D will have exactly the same eigenvalues as the matrix A. The matrix D's characteristic polynomial will be the same as the characteristic polynomial of A. And also, the dimension of the eigenspace corresponding to the eigenvalue lambda of D will be the same as the dimension of the eigenspace corresponding to the eigenvalue lambda in the matrix A. Right, so those things are all going to be the same. So all I have to do basically is I just have to look at determining the algebraic multiplicity of an eigenvalue and the geometric multiplicity. All I have to do is I just have to look at this matrix here, because whatever is true for the matrix D with regards to those properties, it's also going to be the same for the matrix A. So let's just determine the characteristic polynomial of D. So there's the form P lambda. That is the characteristic polynomial of D, and we all know how to get that. So let's look at the eigenvalue D11 and go and determine its algebraic and geometric multiplicity. Right, so the geometric multiplicity of lambda is going to be it's going to be M, right? Right, so there's the algebraic multiplicity of D11. Let's go and determine the geometric multiplicity. So we need to determine we need to go and determine the dimension of the eigenspace corresponding to the value D11. Right, so there we work that matrix out, and remember, to get the dimension of that eigenspace we need to look at the null space. Now if I go and work all these terms out, the number of times lambda minus D11 is a factor of the characteristic polynomial. That is going to, we said that's going to occur m times, right? So therefore what's going to happen is you're going to have you're going to end up with a situation where you're going to have m zeros occurring on the diagonal, because D11 is a factor of the characteristic polynomial exactly m times. So you're going to get a zero there, and you're going to get m zeros. Right, so we're going to, on the diagonal, let's just, on the diagonal, which is that term there, there are going to be, on that diagonal, which is that, okay, there are going to be m zeros. They're going to be m zeros, okay? Now, if you look at the null space, you're going to have to solve that linear system. So you're going to have basically in the null space well, in this linear system, you're going to get zero rows, right? So you're going to get M0 rows. Now remember, the 0 rows correspond to, in your linear system, correspond to the number of free variables. And the number of free variables is actually going to determine your dimension of your null space. Right, so that linear system has m free variables, and so the dimension of the null space is going to be m. And therefore, D11 will have geometric multiplicity m. So the geometric multiplicity of D11 in the matrix D is m, and its algebraic multiplicity is exactly the same. Now, because of that invariant property of the similarity transformation, whatever happens in D will also happen in A. So in A, D11 will also have algebraic multiplicity m, and it will also have geometric multiplicity m. Alright, so basically we showed that given that A is diagonalizable, then the geometric multiplicity of every eigenvalue is exactly the same as its algebraic multiplicity. But it's if and only if, so the reverse is also true. So if the geometric multiplicity of every eigenvalue is exactly the same as the algebraic multiplicity, then A is diagonalizable. Why is that the case? All right, look at it this way. If the geometric multiplicity and the algebraic multiplicity of each eigenvalue are the same, then if we go and look at the characteristic polynomial is going to look like this, right? So it's going to have all these factors, and lambda 1 occurs in this polynomial as a factor exactly n1 times. Lambda 2 occurs n2 times up until lambda n. Now, we said the algebraic and the geometric multiplicity of each one of these eigenvalues is exactly the same. So the eigenspace corresponding to lambda 1 has dimension n1. The eigenspace corresponding to lambda 2 has dimension n2. Up until lambda n, the eigenspace corresponding to lambda n has dimension n subscript n. Now, that means that all these basis vectors, if I throw them all together, it's going to form a linearly independent set. And there are going to be exactly, now this follows from the previous theorems, remember? Eigenvectors corresponding to distinct eigenvalues are linearly independent, and the basis vectors amongst themselves are going to be linearly independent. So if you throw that all together, that's going to be a linearly independent set of eigenvectors. And how many such eigenvectors are there going to be? There are going to be exactly n1 plus n2 up until nn. Eigenvectors, and so that's going to be a linearly independent set of cardinality n, and so it's going to, A has n linearly independent eigenvectors, and there's a theorem that we did which says that if a matrix has n, an n by n matrix, if it has n linearly independent eigenvectors, then it is diagonalizable. Alright, so why is the geometric multiplicity less than or equal to the algebraic multiplicity? Let's, for a specific eigenvalue, let's say the eigenvalue lambda 1. Now what you do is you compose this matrix here and you look at the determinant of that matrix to get your characteristic polynomial. So you can do this by just row reduction. You use two operations. You take a multiple of a row and add it to another row, or you switch rows. You can also do it via columns. You can add a multiple of one column to another. You can you could switch two columns around. The worst that will happen is your determinant will either stay the same on each step, or it will change with -1. So basically, once you've reduced this, you will find the reduced row echelon form with these functions or lambda polynomials on the diagonal. Now, none of these polynomials can be the zero polynomial because that's going to mean that the determinant of this matrix is zero. So that is going to it's going to imply the determinant of that matrix is zero, irrespective of what the values of lambda are. So it's going to imply that your matrix A is going to have infinitely many eigenvalues, which is impossible because we said a characteristic polynomial of the n by n matrix has got at most n roots, so you can get at most n eigenvalues. Right. So therefore, each one of these polynomials it can't be the zero polynomial. So therefore, if we calculate the determinant of the matrix R, that is going to be it's going to be the product of those entries there, and then working backwards, we can then deduce that the characteristic polynomial of A will have this form here. Now, if we look at the eigenvalue lambda 1, now remember the dimension or the geometric multiplicity or the dimension of the eigenspace corresponding to lambda 1 is basically going to be determined by the number of zero rows that you're going to get in this matrix here once you've plugged lambda 1 into the lambda polynomials. So essentially what it means is a zero row will occur only when if a zero row occurs, say in the first row, it means f1 in the point lambda 1 must be 0, and therefore that's going to mean that lambda minus lambda 1 is going to be it's going to be a factor of f1. So it is going that f1 is going to have a factor lambda minus lambda 1, right? Say if the nth lambda polynomial becomes 0 if you plug lambda 1 in there, then again this function here is going to have that as a factor. So now already we've got two factors, one factor in f1 and one factor. This factor I'm talking about. This factor occurs in f1 and in f subscript n lambda. So therefore, again, there in that case, if you have only two zeros that occur in f1 and fn, it's going to mean that the geometric multiplicity is going to be less than or equal to the algebraic multiplicity, because then the dimension is going to be 2. And you're going to have, at least in the characteristic polynomial, this factor occurring twice. And you can do it for more than two zeros. In actual fact, the argument extends the same, extends to a larger number of zeros. So basically, that's an illustration of why the geometric multiplicity is always less than or equal to the algebraic multiplicity. Right, so here's an example. If we take the matrix, A, and it has characteristic polynomial, right? That's the characteristic polynomial. Now, the basis for the eigenspace corresponding to lambda equals 0 has dimension 2, and again that corresponds to the number of times it occurs in the factor. Here, basis for the eigenspace corresponding to lambda equals minus 2 is exactly 1, and that corresponds to the number of times the factor lambda plus 2 occurs in the characteristic equation. Right, so there you can easily see that in that particular case the dimension of each eigenspace is equal to the number of times it occurs in the as a factor in the polynomial. Then again here you've got another example. The matrix A has characteristic equation that, and again the dimension of each one of the eigenspaces is 1, and there the number of times the factor delta minus lambda minus 1 occurs in the characteristic polynomial is 2, so it's 2 is strictly bigger than 1, and there it occurs exactly once, which corresponds to that dimension there. Right, so next we've got some property. If a matrix A is diagonalizable and P diagonalizes A, then we have this nice property, and that is that we can easily go and compute the kth power of A by simply computing that expression there on the right hand side. That can easily be seen if you look at the matrix A to the power of K, then you can easily see that what's going to happen here is these P's are going to reduce to the identity matrix, and eventually you're just going to have equality. Right, so it's not difficult to see why that is in fact the case. Okay, so let's just apply this. Right, so let's use this example as an example of an application of this result. So there we are asked to compute the 10th power of that matrix using what we know so far. So the first thing is we need to quickly establish what the matrix P is, and we need to also look at what the matrix D looks like. Right, so there's the matrix, and this is a upper triangular matrix. Right, so basically the eigenvalues are going to be lambda 2 and lambda equals minus 1. Okay, so those are the eigenvalues. Okay, so let's quickly look at finding the diagonal matrix. Right, so for the first eigenvalue, lambda equals 2, if we go and work this matrix out here, it's going to be 2 minus 2 minus 3. Then it's going to be 2 minus 1, which is 3. All right. So what is the null space of this matrix? We want to take this matrix here, and we want to look at its null space. So you want to go and find all vectors. What do the vectors look like? Such that is equal to 0, and that corresponds to the system. That corresponds to the system y equals 0, and x is some parameter t. Right, so that then becomes all values x, y such that x is t and y is 0, and therefore the basis of the eigenspace corresponding to lambda equals 2 is the vector 1, 0. So now what we do is we look at the case where lambda is minus 1. Right, so working out that equation there, remember what A is. There we go. So basically you take minus 1i minus A So it's basically going to be minus 1, minus 2, which is minus 3. That's going to be a minus 3 there. And then minus 1 minus minus 1, which is minus 1 plus 1, which is 0 there. Right, so we have that, and now it's a question of looking at the null space of the matrix in question. So basically what you're going to do is you're going to look at the null space of that, and that is you're going to take that matrix, determine the null space, and that corresponds to the system where x plus y is equal to 0 and y is a parameter t. Okay, and that corresponds to all vectors such that x is minus t and y is t. Okay, and again that is going to be right. The basis corresponding to lambda equals minus 1 is that vector there. Right, now recall this. Basis of the eigenspace corresponding to lambda equals 2. So your diagonalization matrix is going to be the matrix minus 1, 1 and 1, 0. Your matrix D is going to look like that. It's going to be the diagonal matrix with the eigenvalues on the diagonal. So now we can go and compute the power or the 10th power of A. So the 10th power of A is going to be you're going to take that matrix there. Then you're going to multiply it with the 10th power of that. So it's going to be minus 1 to the power of 10, which is 1, 2 to the power of 10, which is 2 to the power of 10. And what you're going to do is you're going to take that matrix and you're going to multiply it, well, you're going to invert it. Right, so then calculate the inverse of the matrix P, and we have that product. Right, multiplying out the first two matrices, we get this matrix. And working out the last term. And so we get the final matrix there.